Okay, so we are in the midst of chapter 6, which is the quantum chemistry or the quantum mechanics. Yesterday, we looked really just at one type of problem, which was the Heisenberg uncertainty principle, which is a challenging calculation because of all of the units and the different ways in which the problem can be worded. Today, we're going to kind of get a little bit closer to the practical aspect for us in chemistry, which is the distribution of electrons in an atom, because the distribution of electrons in an atom determine its chemical properties. So for example, carbon is capable of forming bonds to as many as 4 different atoms. And so that gives it an enormous flexibility in terms of the types of molecules that it can produce. We see molecules like proteins and nucleic acids like DNA and carbohydrates and complex carbohydrates, which give rise to all of the life on the earth. And that's having to do with the electron distribution, the very specific electron distribution that carbon has. Nitrogen, for example, has also quite a variety of chemical properties. So those of you who have taken biology classes recognize the importance of nitrogen in things like amino acids and proteins and nucleic acids as well, right? But not quite as flexible and not quite as the variety that carbon has. And that has to do with its specific electron distribution. So the goal of the chemist in this matter is to use whatever physical theories we can, and most of these theories were developed by physicists, to figure out how we can predict how elements, how atoms, and how molecules will behave so that we can gain an understanding of molecular structure, things like proteins, things like DNA, things like drugs, but also to be able to design new things, to design molecules such as the mRNA antidote to the vaccine to COVID-19, for example, right? So it takes a molecular understanding to do that, but to gain a molecular understanding of that, we have to have an electronic understanding of how the electrons in those specific atoms in that molecule behave. So that's where we're at right now. So the next step is to start using what we might consider a relatively modern theory of the electron. And so this is, I want to make sure I get this right. This is section 6.6. So we're in section 6.6. Okay, so 6.6 is concerned about what are called atomic orbitals. Okay, sometimes referred to as AOs. So you'll see this term sometimes in the literature, AOs for atomic orbitals. And the term atomic orbital refers to atoms, right? So we're talking about individual atoms. And an orbital is a new word. We haven't used that word before, although we have used the word orbit, right? The word orbit connotes this idea of a trajectory, right? That the electron is orbiting the nucleus of the atom, right? That's the particle component of the electron. An orbital is sort of, the word is built on that. So orbital is different than an orbit, but it sort of connotes the idea of what an orbit is. So here's essentially, in a nutshell, I don't want to go too far into the theory in this. That's something you would do in a more advanced course. An atomic orbital is a probability distribution of an electron around the nucleus. It's a probability distribution. And the reason that we deal with this in terms of probability distributions is that it turns out, because of the Heisenberg uncertainty principle, we cannot know perfectly the position of an electron. So it's useless to consider its exact position. But what we can do is we can talk about the probability that an electron is in a certain space around the nucleus. And so what we end up with are what are called probability distributions. So let me show you one way of representing that. It's graphically. So this is starting at 0. This is the distance of the electron from the nucleus. So it's increasing in this direction, okay? So the further you are to the right, the further away the electron is from the nucleus. And then on the on the y-axis, this is probability, right? So, you know, in terms, quickly about probability, imagine you're rolling dice, one die, and what's the probability that it's gonna, when you roll it, come up as a 2? 1 out of 6, right? Or about 12%, 11%, or 16%, sorry, about 16%. What's the probability to come up a 4? Well, it's the same. It's 1 out of 6, right? There's 6 sides, so the probability that it comes up as a 4 is 1 out of 6, which is about 16%. So that's a probability, right? And so now here's what we get. It turns out that if you study the electron, you get these distributions that looks something like this. It's actually not that different from our Boltzmann distribution when we were talking about gases. It's a little different, but it's not that different, okay? So you get a distribution that looks like that. Now, what does that mean? That means that the probability that the electron is in the nucleus, right? That would be a distance of 0 if the electron was actually in the nucleus. That probability would be very, very small. It's not likely to be in the nucleus, okay? What's the probability that it's very far from the nucleus, like really far? Well, that would be out here, right? And if you look out there, it's almost 0, right? There's almost 0 probability the electron is far from the nucleus. So that means the electron is somewhere in the middle, right? It's like not too close to the nucleus, but not too far from the nucleus, right? It's in between. And that is essentially a probability distribution. And you could say, hey, look, where you get a maximum, that's the most probable distance, right? That's where it's most likely to be. But keep in mind, we're not claiming that it is there. We're claiming that it's anywhere between here and here. And we cannot know where it is in that. All we can say is that it's somewhere in that region. So notice we're giving up a lot of the sort of what we call classical physics aspect of this. And you might say, well, why is this even useful? We'll talk about why it's useful in a moment. It turns out if you measure and do calculations for the hydrogen atom, this distance, this most probable distance, just to come down here, is about 0.53 angstroms. And I mentioned the angstrom yesterday. This would be 5.3 times 10 to the minus 11 meters. Is that right? Yeah. Okay. Oh, I'm sorry. Is it 0.53? I'm sorry. It's 0.53. That's right. So pretty small, right? That's the most probable distance. And the electron can be further away. It can be closer, but it's not likely to be 0, and it's not likely to be very, very, very large. Okay. So that's our idea of a probability distribution. Now, the atomic orbital, the AO, is essentially the probability distribution. It's the probability distribution of the electron in the atom. And so it's generally, for us, from a chemist perspective, we could represent it like this, and we sometimes do. You're going to see this in your textbook and stuff like that. More likely, we're going to do it as a diagram, as like a little cartoon, if you want to use that term. And it's usually represented like this. Okay, something like that. And the interpretation of this picture is this is the nucleus. That's at the center of the atom, right? So that's the nucleus. And then this region out here, or I shouldn't say region, this little boundary, if you want to call it that, that dashed line that I'm drawing, That is what we would call 90% probability surface. So that's where what we're claiming is that anything inside of that barrier is 90% of the probability. So meaning we're essentially taking up 90% of this. We're going to go out to about right there. So not 100%. And the reason we don't do 100% is 100% mathematically is all the way out here. 100% is almost infinite. So for that reason, we just kind of stop at 90%. So 90% of the probability would be on this boundary surface right there. And sometimes it's drawn as a dashed line. Sometimes it's drawn as a bold line, okay? And so really what we're claiming now is the electron is 90% probability that it's in that space. And for the most part, that works for us. We only need to know what the most likely region of space it's in. And that space in there, it's a volume, right? I'm drawing it as a circle, but it's actually a sphere. It's three-dimensional. This is called an atomic orbital. Okay? That's the atomic orbital. So what we're claiming is the electron is in that orbital, right? It's in that space. Now, what we're also going to claim is that there are many different types of orbitals that exist in atoms. And again, we can't go through this in this course because it's a more advanced topic. All we can do is really show you the results because we're not going to go through the mathematics. So when it has this particular shape, it's called an s orbital. So remember, that's a probability distribution. We're claiming that 90% probability that the electron's in that space. That's called an s orbital. So if it looks like that, it's an s. But there are other types of orbitals as well. The atom, the electron, has the ability to have different probability distributions. So look at this one. This one's different. And I'm not very good artist at this, but I'm trying to draw two regions of space that are symmetric so they look like each other, right? The nucleus is right here in the center. There we go. That's a little better, right? I'm trying to make them the same size. I'm not very good, particularly on this whiteboard. A little bit better on it on a piece of chalk. There we go. Okay. So there's the nucleus again, right there in the center. Remember, in an atom, the nucleus is in the center. This is called a p orbital. Okay. Now notice it has two what are called lobes. Right? So this is one lobe right here. And then this is a second lobe on the right. And now that's the probability distribution, which means the electron is occupying those two, if you want to consider it two spaces, simultaneously. So the electron is no longer thought of as a particle as moving around and jumping from one spot to another. It's occupying that region of space simultaneously, like a wave spreads out, right? As I talk, the sound waves that are coming out of my vocal cords are spreading out across the room, right? This electron is spreading out across these two regions of space. And it's a vibration. It's a vibration of the electric field that the electron creates and the magnetic field that the electron creates. It's a vibration, okay? That's called a p orbital. And there's a second one. There's a third one that we might be concerned with. And this one actually has the ability to have two shapes. So I'm going to show you both shapes. And I'm going to refer you to textbooks if you want better quality drawings than I can give you. This one has 4 lobes, and it's called a d orbital. And it has 4 lobes. So in a sense, there's the nucleus at the center, right? The nucleus is always in the center in these orbitals. Any electron that's in this orbital is undergoing some sort of vibration such that it occupies all 4 of these spaces. And these things are real. I mean, we actually have very good evidence for them, because you can do these little experiments with light, with lasers, where you shine lasers, and lasers have a particular physics of how the light is formed. And so they follow the same dynamics. It's right. It's wave dynamics. And you can actually like shine these laser beams onto a surface and actually see these shapes. They come out just like this. Sometimes they're like, you know, like a sphere. Sometimes they're 2 lobes. Sometimes they're 4 lobes. It's following the same mathematics that the electron is following. So you get these shapes. The one thing to remind ourselves, though, is that this is 3-dimensional. I'm depicting it as a 2-dimensional phenomenon, but it's actually 3. Nucleus at the center. And now I said the d orbital, actually, for reasons that are kind of beyond the scope of this class, actually has 2 shapes. So there's this shape where you have 4 lobes, and then there's a second shape that's possible where it has 2 lobes. The nucleus is in the center, but then it has a third region here in the center. You know, almost like a planet, right? Like Saturn, where you know how Saturn has rings. So here's your nucleus at the center. You've got 2 lobes, and then you've got this little disk. It's not actually a disk. A disk is 2-dimensional. It's a toroid, so it's like a bagel or a donut. It's actually 3-dimensional. There in the middle. So this one is also a d orbital, and that just has to do with the nature of the mathematics. Nature appears to obey mathematics. So if you go through certain mathematical functions, you get this shape, and it turns out that the electron actually occupies this kind of spatial region as well. So these are all called orbitals. They're S, P, D, F. We're going to talk about the notation of all that. There's one more aspect of these orbitals that I want to point out, and that has to do with waves, and that is what's called a node, or a nodal plane. So it turns out through the nucleus, the probability that the electron is in that space is 0. And a node is where a wave has 0 amplitude, so 0 probability. So it turns out the s orbital doesn't have any nodes for this one. This one has 1 node, and then this one has 2 nodes. And just to show you kind of mathematically what a node is, if you take a wave, like a sine wave, the node is where the amplitude is 0. So these would be nodes right there. Okay, so the wave doesn't have any height there, and the amplitude is 0. So same thing here. In that space in between these lobes, if you want to think of it that way, there aren't any. Okay, so that's a brief intro. Now what we're going to claim is that the electron is in these spaces. So it might be in this space right here. It might be in this space over here. It might be in this space over here. It might be in this space over here. But if we give energy to an electron, it could move from one space to another, a transition. Remember, Bohr talked about that. You have these energy levels, and the electron can go from one level to another. That's still true. We know that's true. So that means that it's possible for you to put energy into an atom and promote the electron from one orbital to another. So you could go from the S to the P, or you could go from the D to the P. There's certain allowed transitions that can occur. So before I go into that, let me talk a little bit more about energy levels. I'm going to save that because I actually did some drawing on it. Okay, so let's come back to this issue of energy levels. Right? Remember with Bohr, we said we had n equals 1, 2, 3, 4, 5, 6, ... Well, that's true. There's nothing wrong with that claim. There is actually a quantum number for these waves that corresponds to energy, and that energy is quantized. It has different levels. So that's true. Bohr's insight into the quantized energy levels was absolutely spot on. He just didn't understand that the reason for that is that they're behaving like waves, like strings on a guitar or a violin or a drum, right? A membrane on a drum. He didn't understand that, but he was correct about these energy levels. So it turns out these orbitals have energy levels as well. So we talk about orbital energies. And so the first thing I'm going to do is I'm going to show you a picture. So I'm going to do it this way. Let me draw that a little bit better. I'm going to draw an energy level diagram, just like we've done before. So this is energy, right? And we're going to start at the lowest energy. The lowest energy orbital, and I'm going to draw little pictures of these orbitals. So there's your first orbital. This is an s orbital, right? S is the little sphere, and it's in the first level, n equals 1. So I'm going to call it a 1s orbital, right? 1 meaning it's in n equals 1. So that means n equals 1, which is the lowest possible value for n. And we're claiming it's an s orbital. Okay. The second one, the one that's higher in energy, is a bigger orbital. So I drew it a little, let me draw it even a little larger. There we go. See how it's bigger? So what happens is when an electron has more energy, the wave gets bigger. And so the orbital gets bigger, right? Waves can have different sizes, right? Think about water on the ocean. You can have these little waves if the water's tranquil, but you can also have these big waves, right? So same thing here is the wave gets larger, the vibration is larger, it has more energy. That kind of makes sense, right? A big wave has more energy than a small wave. So this is 2, and the shape is the same, right? So it's a 2s. So here we're claiming n equals 2. And again, it's an s orbital, right? Now, the third orbital, a little bit higher in energy, is a 2p orbital. So I'm going to draw it this way. Okay, so this is also 2, n equals 2, but it's a p orbital, right? So that means n equals 2. I'm going to go over how you figure out the order of this later, but I just wanted to show you what they look like. Okay, so the third one is a 2p. And then the next one is a 3s.
Professor said it's p orbital, but
yeah.
you wrote s orbital.
Oops, thank you. Good. Good catch. 3s, n equals 3, and then again, this is an s orbital. Let me use my same notation there. Comma s orbital. So again, notice how the 3s is larger than the 2s, which is larger than the 1s. So the orbital is getting bigger and bigger. Now the significance of that is that means that if the electron is in one of these orbitals, it's further away from the nucleus. And so what happens when an electron is further from the nucleus? The atom is larger, so it makes the atom larger, but it also makes that electron less held by the nucleus, right? The further away the electron is, the less tightly held by the nucleus it is, which makes it more interested in interacting with other atoms because it's further away from its own nucleus. So it changes the chemistry based on that. So there's your 3s. The next one is a 3p. Now the 3p ends up being pretty difficult to draw, but I'm going to draw it this way. It has 2 lobes, like a 2p does, but then it has another region out here. So the general shape's the same, right? The nucleus is here in the center. This right here is a nodal plane. That's where the amplitude is 0. But generally, you can just sort of think of it as larger. It's all the way out here, all the way out here. So that's a 3p. So what is n? If I call it a 3p, that just is telling me that n is 3, and that's a p orbital. Okay. Now you can sort of see that what happens is this starts to be a pretty big diagram. So I'm going to show you a shorthand notation for it without drawing the pictures. the take home from this is that the lowest energy level possible for the electron is 1s. And so again, just like with the Bohr model, we call that the ground state, right? The ground state is the lowest energy. Well, the 1s is the lowest energy. That's as low as the energy of an electron can have. It can't be in a smaller orbital than a 1s. It can't be in a different shape than the 1s. If it's at its minimum energy, it's going to be in the 1s. But it can also exist in different levels. It could be in a 2s or a 2p. So it's possible if I put energy in, I could move the electron from the 1s orbital. I could move it up to the 2p, for example, right? I could put in energy and have it do that. And now that electron would be behaving differently. It would be a different kind of vibration. It would have two lobes. And actually that, that leads to certain interesting aspects. It leads to the possibility that this atom could bond to another atom over here, but it could also bond to another atom over there. So it has the possibility of bonding to two different atoms, So it leads to interesting aspects when we get into the bonding. Okay. So now, like I said, these diagrams are pretty complicated looking, but what I want you to be able to do is to be able to look at an orbital and recognize, oh, that's an s orbital, or that's a p orbital, or that's a d orbital, and that these orbitals have different energies, and that in general, as n goes up, the energy goes up, right? The 3 is higher than the 2, and the 2 is higher than the 1. So as n goes up, energy goes up. The other take home is that if n is the same, the p has more energy than the s, right? So the 2p has more energy than the 2s. A 3p has more energy than the 3s. Okay, so let me write that as let me just write that down. So as n increases, the energy increases. And then if n is the same, the energy of a p orbital is greater than the energy of an s orbital. And you can go even further. The energy of a d orbital is greater than the energy of a p, which is greater than the energy of an s. So now you have an ordering system for the energies of these orbitals. Okay, so what chemists and physicists do is they calculate all of these atomic orbitals, and that was done. Gosh, I guess it was done almost 100 years ago. It was done in the 1920s, the late 1920s, or mid 1920s, so almost 100 years ago. And these energies are now understood. We understand what these energies are. We know what they are. They can be measured and calculated and all that. So I'm going to show you a diagram of the energies. I'm not going to draw the pictures anymore. I'm just going to label them. So there's energy. So the lowest level, again, that's the ground state, is the 1s orbital. Okay, so notice I have a little line there. So that's just to mark off on the vertical axis how much energy that particular orbital has. And then the next one up is the 2s. And then the next one up is the 2p. But now I'm going to show you something interesting. It turns out that for the p orbitals, there are 3 possible orbitals. And that makes them different than s orbitals. So I'm going to represent that with 1, 2, 3 different lines. Okay. Now, what's the reason for that? The reason is that once something gets up to a p orbital, once it has that amount of energy, it also has something called angular momentum. And there are 3 possible angular momentums that this particular orbital can have. It can have a vertical, so it's vertical. It can have a horizontal, and it can also have a coming in and out. So this is also horizontal. So the x, if you want to think about it this way, x, y, z, you could think of it that way. There's 3 different possibilities. So there's 3 different waves, or wave functions, we call that. So remember that for the p, there's 3 orbitals, not just 1. And the electron can be in any of those three. It could be in one or the other or the third one. Now, once you get beyond the 2p, the next one is the 3s. So this is just like the previous slide that I showed you. So there's your 3s. And then 3p. And then remember, p's have three possibilities. And then the next one is the 4s. And then the next one is the d. That's our first d. And that's called 3d. Okay? So remember the D, just to remind you, was the one where you had your 4 lobes. Or you had the 2 lobes with the toroid in the middle, right? So those were your d orbitals. Those are the shapes of those ones, okay? So notice there's 5 of them, right? Just like with the P, there's different combinations and different orientations that are possible. It turns out with the D, you get 5, okay? So what's the next one? The next one is 4p. And then the next one is 5s. And then the next one is 4d. And then I'm running out of room up here. So let's do this one. Then the next one is 5p. And then the next one is 6s. And then the next one is 1, 2. I'm going to stop right there, okay? I'm going to stop right there. Actually, I'm not going to do this last one because it involves the f orbitals, and I'm not going to go through the f orbitals right now. If we need to do that later, we'll talk about it. So these do continue. The n value gets larger and larger and larger, 7, 8, 9. It turns out in practice, as atoms become more and more complicated, eventually they become unstable. And so for the most part, you can't go much further than this before the atom becomes unstable. It just doesn't exist for very long. So we usually don't have to go that far. For those of us that are working in things like biology or standard chemistry, like organic chemistry, we usually don't need to go beyond here. That's usually where we're going to go. We're not going to worry about things beyond that, but these ones are shown here. So how did I know that? How did I know the order? I memorized the order is what I did. But there is actually a little way to kind of help yourself know the order. And I'm going to show that to you. It's in your textbook, and it's in most textbooks. So what you do is this. You write all the S's, and you just write it increasing n as you go up. And you can go as far up as you want. That's fine. But like I said, 6 or 7 is as far as you need to go. And then next to it, you start at the second level and you put the P's. Same thing. You just go 4p, 5p. Remember, going vertically is generally higher energy. And if you want to go to 7p, you can do that too. But we're not going to need it for now. And then in the third level, you start with the D's. Okay. Now, for some kind of exotic problems, the F becomes important. So for example, gold has F orbitals. So I'm going to start here by putting your F's in here. But as far as I know, there aren't any elements in the periodic table that have anything beyond 5F. So I'm going to stop right there. Okay. So now here's how you do it. This is to get the energy order. What you do is you start right here at the bottom. And the tricky part is you want to draw a horizontal, I'm sorry, a diagonal line, right? So you start with the 1s. So I'm going to write 1s down here. Then you tail it back here and do it again, another diagonal. And then you tail it back and you go this way, a diagonal. So notice now I've got 2p3s. And then you tail it back and you do it again, 3p4s. And then you tail it back, and now you got 3d, 4p, 5s. And then you come back here, 4D, 5P, 6S. And then the same thing here, 4F, 5D, 6P. So look, I'm running out of room here. See how long these things are? So then it's 6S, and then it's 4F, and then 5D, and then 6P, and then 7S. And if you want to even go further, you can, again, tail it back and go this way. So 5F, 6D, 7P. And so that's your energy of, that's the order of energies. So you're at your lowest energy here, and then you're increasing energy in this direction. So notice I drew it horizontally instead of vertically. Sometimes you'll see it horizontally, sometimes you'll see it vertically. So this is increasing energy. Okay. Now, why is this important? It's important because atoms have more than one electron, and it's going to lead us into this whole energy filling idea. Just in a nutshell, essentially what happens is there's a maximum number of electrons that can fit into an orbital. So once that's filled, any additional electrons have to go to the next orbital. And once that's filled, they have to go into the next ones, and so forth and so on. So those electrons are going to fill up those orbitals from the 1s all the way up to, if you have enough electrons, all the way up to 7p. Okay, we're going to do that when we do electron configurations at the end of the chapter. Okay, the Alex is going to ask you a few questions about how you get or how you use this notation in terms of like counting electrons and quantum numbers and all of that. So let me spend the rest of the time today kind of talking you through how to do some of those problems. Okay. So let's begin by introducing what are called quantum numbers. You are familiar with what the first one, this is called n. And n is what's called the principal AL, quantum number. Okay. This tells us the energy of the orbital. Okay, tells us how much energy it has, right? Going back a couple of slides, remember 1s, 2s, 3s. The lower the value of n, the less energy it has, the higher the value, the more energy it has. Okay, what are the possible values for n? N can equal 1, not 0, 2, 3, 4, 5, 6, 7. How far do you want to go? We don't generally need to go more than 7. Some physicists will do experiments where they try to move an electron from like the 18th level up to the 20th level, that kind of stuff. And you can do it. It's really cool experiments. But for us, we usually don't need to worry about more than 4 or 5. Okay. The second quantum number has the symbol L, but it's got to be a lowercase L. It can't be an uppercase L. So that's complicated. How do you do a lowercase L so it doesn't look like a 1? So usually the way we deal with that is we make it a script L, a lowercase L. Okay, so it looks like that. The problem is that if you do an uppercase, it has a different meaning. So this is called, it has different names. It's generally called the orbital, I'm sorry, the angular orbital. Angular momentum quantum number. Okay, and what does this do? It tells us the shape of the orbital. The shape. Okay, its possible values are, it can be 0, 1, 2, 3, 4, 5, 6, but it has a maximum value of n minus 1. It can never be as large as n. So let's say n is 6. L could be 0, 1, 2, 3, 4, 5. N minus 1 is 6 minus 1, that's 5. So the highest it could be is 5, but it could be 0 or 1 or 2 or 3 or 4. Now, what does that mean, the shape? That's not as obvious, but you actually already know. we know what the shapes are, right? We've got this one here. There's your s orbital, right? S is the case where L equals 0. That's what an s orbital is. It's the case where L equals 0, this angular momentum quantum number. So a shape like that has a certain amount of angular momentum. A shape like that has a different amount of angular momentum, right? So if we do, oops, oh wow, we're running, oh, that's not, okay. So we're running, let's do this one. There's your P, right? That's the one we talked about earlier. There's your P. This is the case where L equals 1. Okay. And then we talked about the D. The D is the one with 4 lobes, right? This is the case where L equals 2. And I'm going to go ahead and do the F. Let's put the F in here. The F is even more complicated. It actually has 6 of these lobes. So it looks like a flower, right? It actually looks like a flower. L equals 3. Okay. So the difference between an s orbital and a p orbital is the shape, but mathematically the difference is the value of L. Okay. So it's often recommended that people memorize this. S, P, D, F is 0, 1, 2, 3. So there's your L, and then there's your name of the orbital. And I'm not going to go through the whole notation of why it's SPDF. It has to do with some of the history of physics, okay? So that's your second quantum number. There's a third one, and it's called M sub L. So lowercase m, lowercase l. This one's called the magnetic quantum number. It actually has a couple different names, just like the angular momentum quantum number has. But we'll use the simple name. Okay, M for magnetic, right? Notice it has an L as a subscript. That tells you, oh, it must somehow be related to L, and it is actually. This shows you the direction of the orbital, what direction it's pointing. And sometimes that's referred to as orientation. Okay, the orientation is the direction. And this one, M sub L, can be 0, but it can also be negative. It's the first quantum number that can be negative. Oops, sorry. It can be positive or negative. But the highest it can be is L. It can never be greater than L. So let's say that L is 4. M sub L could be 0, plus 1, plus 2, plus 3, plus 4. It has to stop at L. But it can also be minus 1, minus 2, minus 3, minus 4. It has to stop at minus L as well. So it can never be greater than L. That's different than the L. Remember, the L can never be as big as N, right? It's N minus 1. So if N is 3, L can only be up to 2. If L is 3, M sub L could be 3. But it could also be minus 3 or minus 2 or minus 1 or 0 or plus 1 or plus 2. So it has a lot of different values. So what does that mean? The direction. Remember when I talked about the p orbital? How the p orbital has 3 different directions? Oops, I drew the third one, just like the first one. So let's do this way. So sometimes they're actually given names like px, py, and pz to indicate that they're in different directions. So the value of M sub L is telling you something about the direction. The more possible values you have for M sub L, the more directions that are possible. So as L goes up, the possible directions goes up. So there's your first 3 quantum numbers. Energy is N. Shape is L. Direction is M sub L. And they follow these mathematical rules. But there's one more quantum number that we need to be familiar with, and that one is M sub S. So this is your 4th quantum number. This one is called the magnetic spin quantum number. So notice it also has an M, but it's got a subscript S for spin. Okay, spin. This is a property of the electron. It's not actually the property of an atom as much as it is the electron. Electrons in atoms behave as though they spin. Okay, so I'm going to be very careful about this. We're not claiming they spin, they just behave as though they do spin. So they create a magnetic field that is representative of them spinning, okay, as if they were spinning. So M sub s can be spin up. And so if it's spin up, M sub s is plus a half. So it actually has the ability to be a fraction. The electron has a fractional quantum number. It can be what's called spin down. And in that case, it's minus a half. Spin up, you represent that with an arrow pointing up. Spin down, you represent that with an arrow pointing down, okay? We're going to get to the meaning of this in a little bit, I mean tomorrow. But for right now, those are your 4 quantum numbers. Let me save this one. So the first one is the principal energy. Second one, angular momentum, which is the shape. Third one is magnetic quantum number, which is the direction the orbital is pointing. So all those 3 are just about what's the orbital look like and how much energy does it have. The fourth one is each electron is going to have a particular spin, and it's going to be either spin up or it's going to be spin down. And again, we'll see the importance of this probably tomorrow. If not tomorrow, then we'll definitely see it next week early. Okay, so now let's take a look at a problem here. Okay, so the first Alex problem I want to look at is what's called deducing N and L from a subshell label. So they're going to give you a subshell label. So the subshell label is a number with a letter. So 6S, a number with a letter, 3D, a number with a letter, a number with a letter, okay? And then what you want to do is you want to figure out what the value of N is, and you want to figure out what the value of L is. It's very simple, okay? Here's how you go about doing it. The number is N, right? In this notation, N is the number that's given. So you can just write that number in, right? So that means N equals 6. That's a pretty high level, right? That's high energy. 1, 2, 3, 4, 5, 6. 3, that's lower, right? That's lower in energy. 3 is lower than 6. 4 is between 3 and 6. That's really high, right? Once you get up to 7p, that's a pretty high energy orbital. It's way far from the nucleus. It's a big vibration further from the nucleus. So there's your N. What about L? This one's a little trickier, but not that hard. Just remember this, S, P, D, F, 0, 1, 2, 3, right? Remember the L can be 0 and it can never be more than, it can never be as big as N. So if N is 7, the highest value that L could be would be 6, but it could be anywhere from 0 to 6, okay? So there's an S, well, that's 0. There's a D, D is 2. There's a P, P is 1. There's a P, P is 1, and you got it right there. That's really simple to do. But it's important as you go through this to kind of think a little bit, reflect on a bit about what it means. It's saying that, look, this particular subshell involves orbitals that have a lot of energy, very far from the nucleus, and not much of angular momentum. So it's that simple shape, right? The simple spherical shape, which is the s orbital, right? So 6s, high energy. So the reason it's not n minus 1 is that it's a series. So when we say that L equals 0, 1, 2, 3, 4, all the way up to n minus 1, we're not claiming it is n minus 1. We're claiming it could be anything up to n minus 1. So if n is 7, that means L could be either 0 or 1 or 2 or 3 or 4 or 5 or 6. You just can't go beyond 6. But it could be any of these. Yeah, it could be any. And that's the meaning of this. If it turns out it's a 0, you know you have an s orbital. If it turns out it's a 1, you know you have a p orbital. If it turns out that it's a 2, now you know you have a d orbital. It's kind of cool. That's a great question. Okay, let's take a look at another one. So the next type of problem they ask you to do is deducing the allowed quantum numbers. So deducing allowed quantum numbers in an atomic electron. Okay. And so what they're going to do is they're going to say, hey, suppose you have a 2p electron. So that's an electron in a 2p orbital. What are the possible values of m sub L? Okay, so I'll write our answer over here. Okay. Generally, when you give an answer like this, if there's more than one answer, you want to probably separate them by commas. Okay. So let's figure out, let's analyze this. Here's what we know. Here's our notation. This is called subshell notation, right? So we know n equals 2, right? That's the 2. And then it's a p, right? So that means we know what L is, right? So let me rewrite it over here, S, P, D, F, 0, 1, 2, 3. So since it's a p, we know that L is equal to 1. Now, think of it like a hierarchy, right? I often, for me, just to make it simple for myself, I think of an apartment building. You know how an apartment building has an address, so like it might be 645 is the address. That's the street number, but then you've got floors, right? So you got, floor 1, 2, 3, 4, 5, 6, and then you got individual apartments in them. So it might be A, B, C, D, right? And then if you want to know, what the possible apartments someone are in, well, if you know this and you know it's on the 6th floor, you know all the possible apartments. So in a way, that's what this is doing. So think of it this way. You got N, and then you got L, and then you got M sub L, and then you got M sub S. Those are sort of the order. So you start with N. If you got N, that tells you L can only be 0 or 1, right? It could be 0 all the way up to N minus 1, but they already told us that it's 1. So now M sub L, it goes in the following way. All the way up to plus or minus L, right? So what is L? L is 1. So that means what you do is you say this. M sub L has to stop right here. But it's going to start. You always start at the lowest possible value. So you start here. So it can always be 0. That's a possibility. But you stop at where L is, because L is 1, so you stop at 1. So that means you're going to take these first 3 values. So you've got 0 and plus or minus 1. Now, most likely, when you enter this into a computer, they're probably going to want you to enter it in a particular way. So one way would be to say, hey, let's start at the minimum value. The smallest value is minus 1. So minus 1. And then just go up. Right? So if this is a possibility, 0, and these are both possibilities, just go minus 1, comma, 0, comma, plus 1, right? I mean, in theory, there's nothing wrong with writing, 0, comma, minus 1, comma, plus 1, but usually they want you to go in the order from smallest to largest. Okay, let me show you another example. Okay, I'm going to. Okay, good. So same one. So now they want you to list M sub L values for a 3D electron. And I should say these are possible values, right? Because we don't know exactly where the electron is. It could be in any of these spaces, any of these orbitals, okay? So let's take a look. 3D, so we know that n equals 3, and then there's your D. So D is L equals 2, right? SPDF, 0, 1, 2, 3. Okay, so L is 2. So here's what we do. M sub L is 0 plus or minus 1 plus or minus 2. Be careful. M sub L goes all the way to plus or minus L, not L minus 1. It's the L that goes up to n minus 1, but the M sub L goes to plus or minus L. So since L is 2, we're going to stop at plus or minus 2. So how do we write this as a list? Generally, you want to go from the negative to the positive. So I'm just reordering it so that it goes from negative to positive. And you do want to put the pluses. Don't just put 1, 2. Put plus 1, plus 2. And isn't this confusing? Now we're talking about these being quantum numbers. These are not charges, right? They're not oxidation numbers. They're not charges. There's a lot of different notations. And that just really has to do with just the way that the nature of science is, that we have a limited alphabet. We have a numerical system. We could make it more complicated by using Arabic numbers, by using Roman numerals, but we already did that with naming compounds like iron 3 oxide, right? So it's just the idea. The negative doesn't mean anything about negative charge. It's just a quantum number that's indicating something about that vibration. There's an aspect, a magnetic property of that vibration that gives rise to a negative value, okay? So let's take a look at a different one. So another type of question is where they ask you to write out the capacity of electron subshells. How many electrons can fit into these subshells? And it's actually relatively simple. I'm going to give you the answer to that. So it's 2n squared. So for each subshell, the max is equal to 2n squared. So you just take the value of n, okay? So let's take a look at this problem. What they do is they give you the name of a subshell. So you get 3p, 4p, 5s, and then they give you the value. You now have to figure out what n is. You have to figure out what L is, but we've done that. That's easy. And then the max number of electrons. Okay, so let's go through it. 3p, that means n equals 3. SPDF, so L is equal to 1, right? 0, 1, 2, 3. 4p, n is equal to 4. It's a p again, so that's a 1. 5, n equals 5. Remember, it's SPDF, so 0, 1, 2, 3, so that's a 0. Okay, that's easy. Now let's just use 2n squared. Okay, so in the first one, oh, sorry, I'm sorry. We can't use this formula for this. Is that right? Yeah, we can't use that. That's going to give you, that's for a shell. I'm sorry. We're going to have to do this the hard way. Okay, so here's how we do it. I have to give you a piece of information I haven't given you. First, you need to know how many orbitals there are. Okay, so 1, number of orbitals in a subshell. Okay, here's how it works. The number of orbitals in a subshell, if it's an S, there's just 1 orbital. That was in the diagrams I showed earlier. P, there's 3. Remember the horizontal lines I drew? D is 5, and then F is 7. So that's the number of orbitals. Now you need second rule. Maximum 2 electrons per orbital. And we're going to talk about that tomorrow. I'll talk more about that, why that's the case. It's an important thing. But I'm just going to tell you just so you can do this problem right now. So just memorize these numbers, 1, 3, 5, 7. Notice it's just adding by 2. You start at 1 and then add 2. The next letter in the sequence would be a G, and that would be 9. And then an H would be 11. But you don't need those. I'm just kind of showing you. Just add 2 more. So the number of orbitals is 1, 3, 5, 7, 9, 11. But you can have 2 electrons, up to 2 electrons in each one. So think about it this way. If you have 1 orbital and you can have 2 electrons in it, that gives you 2 electrons, right? 1 times 2. If you have 3 orbitals and each orbital can have 2, that'd be 3 times 2, which is 6. If you have 5 and each one can have 2, that's 5 times 2 is 10. And so what you end up with are these numbers here. Okay. I got that right? 11 times 2 is 22. Okay. So now you just, to do this, you just say, look, 3p, it's a p. So p, the maximum number of electrons is 6. Second one is a p, maximum number of electrons is 6. It's an s, maximum number of electrons is a 2. So suppose I gave you one more. Suppose I said it was like a 7f. You would just say, look, it's an f. Maximum number of electrons is 14. And then n equals 7. And L is equal to SPDF is 3. Yeah. Okay. And so there you go. So I actually gave you the wrong formula. The 2n squared is for all of the subshells within one particular shell. So you can't use it for this one. You have to just use this little system here. 2, 6, 10, 14, 18, and 22. But they're not going to give you G's or H's. Don't worry about those. They're just going to give you, looks like they just give SPD. I don't think they even give you F. Oh, they do give you F. So 5F is one example. 5F, if it's an F, it's 14 electrons maximum. Okay. All right. So it looks like there's one more problem in here in this section that I didn't do. So we'll go over that tomorrow and then do 6.7, which is recognizing, we did actually 6.7 already, to be honest with you. And then we'll get into 6.8. So we may finish tomorrow. If we don't finish tomorrow, then we'll finish on Tuesday. But we're moving along pretty good here. We're almost done with chapter 6. It's a lot of stuff that we went through and very different kinds of questions, but it's kind of cool. We're getting closer. Once we get to chapter 8, then we can start talking about chemical bonding. And that's where it really gets interesting, how we can do these Lewis structures and stuff like that. But it's all based on these quantum numbers, and it's all based on counting electrons so that we can get to that point. Okay, almost there. Okay, guys, so have a great day. And I just want to let you know that I did post yesterday's on YouTube, but I didn't make the announcement on Blackboard. So this morning I'll make an announcement on Blackboard and post yesterday's recording and today, but yesterday's is already on Blackboard. Okay, so have a great day. Reach out to me if you have any questions, and be well.
Thank you, Professor.
Thank you. Have a great day.
Bye-bye.